Welcome everybody to Integrated Math 3. In today's episode, we're going to be starting Chapter 3 with 3.1.1 Equation Solving Strategies. Now, this is probably one of the more important chapters in the first quarter of Integrated 3 because in this chapter entirely, we're going to be getting into a lot of different ways to view how to solve an equation, probably some ways that you probably didn't think were possible. So without further ado, let's go ahead and just get started with the first method that doesn't seem very intuitive, but hopefully it'll make sense as we get through it. It's solving an equation graphically. And this kind of boils into the notion that any equation that you solve has a graphical interpretation attached to it. So the problem 3-1 reads, one of the big ideas of chapter 2 was to determine special points on the graph of a function. For example, you use the equation of a parabola written in graphing form to locate its vertex without graphing. But what about the locations of other points on the parabola? Consider the graph of y equals this thing at the right. Now, I've also blown up this image. These two images are the same. It says explore the graph using Desmos and then blah, blah, blah. So it says how many solutions does the equation y equals this thing have? And how's that shown on the graph? So remember, when we talk about the solution to a quadratic function, the solution to the quadratic function will be what happens when y equals 0, right? So if 0 equaled x plus 3 squared minus 5, how many solutions would that produce? Well, let's find out where 0 is. When y is 0, what you're dealing with is an x-intercept. So basically, what A is trying to ask you is how many x-intercepts does this parabola have? And it really has 2, right? I mean, we can see it right here. It's right here and right here. So that would be 2 solutions. 2 solutions, right, to this quadratic equation. Now it says, how many solutions does the equation x plus 3 squared minus 5 equals 4 have? And how is this shown on the graph? Well, remember, if we do x plus 3 squared minus 5 equals 4, what we're trying to find out graphically is where this parabola crosses through this horizontal line. So what I'm going to do is I'm going to take a different color here. I'm going to go and draw in a horizontal line at 4. And again, there are 2 solutions right here and right here. And it says use the graph to solve the equation and then all that stuff. Okay, cool. So then this is going to happen at x equals, well, if I look at it, it looks like x equals negative 6. And it happens at x equals 0. So that would be the solution to the equation x plus 3 squared minus 5 is equal to 4. So hopefully that makes sense when we are interpreting the results of an equation in a graphical setting. I'll be right back with problem 3-2. In 3-2, it says the graph in 3-1 was useful to solve an equation, but what if you don't have an accurate graph? And what can you do when the solution is not on the grid or is off a point on your graph? In these cases, algebraic strategies are useful. It says solve the equations below using 3 different ways. The discussion points below are provided to get you started. So let's go and take care of one of them. Anyways, I think that no matter what I'm going to do, now of course, one method is I could just graph this thing, right? I could just say, all right, if I had Desmos readily at my side, I could just graph both like I have, and then see where the points of intersection are, which would be this negative 7, 11, and 1, 11. So that would be one strategy. I mean, if we had the technology available to us. Another strategy that we could use will be to simply add 5 to both sides. So if I started off with that, so if I add 5 to both sides, that'll be 11 plus 5, which is 16. Now at this point, this is where methods 2 and 3 kind of come into play. If I use method 2, so I'll say method, I won't even call it, name by numbers, method, I'll call this one looking inside. Now we have experienced this across the last 2 integrated sections. We used looking inside in integrated 1 to solve some absolute value problems. We used looking inside as an introduction to how to solve a quadratic equation when we first started learning quadratics in integrated 2. And what it does is it says, well, what can x be in order to make the outside 16? In other words, if I take x and I add it to 3 and then I square it, what could be, what number would have to be on the inside to make this thing 16? Well, I know that the inside would have to either be a -4 or it would have to be a +4, because either one of those iterations squared would end up being 16. Now, that's not to say that x has to be negative or +4. That would be wrong. But if x was equal to 1, right, 1 plus 3 would be 4, and then squared would get me 16. Now, in order to make this thing a -4, x would have to be -7, because -7 plus 3 is -4. If I square that -4, I get a 16. Now, honestly, the looking inside method is not, in my opinion, your best weapon. I really think hardcore algebraic undoing is going to be the style that you want to use. And that's what this book calls it. It's the undoing method. And so from here, if you start off with x plus 3 squared equals 16, if you square root either side, that'll undo the square. So you get x plus 3 equals, now here's where you got to be careful, because remember, this is kind of related to the looking inside method. The 16 does not just become a 4, it becomes plus or minus 4, and that's because the inside could have actually, again, been the -4 or the +4. The other way of looking at this is that if you square root the square, what you get is you get the absolute value of x plus 3, which is in fact the positive and negative version of the inside, which is exactly what the looking inside method was trying to get us to see the whole time. So a number of different ways of looking at this. And so from here, I'm going to go ahead and say x plus 3 equals 4, x plus 3 equals -4, and that was just my mail delivered if you heard that commotion in the back. X equals 1, x equals -7. And again, the method ends up producing the same answer. So hopefully that makes sense. I'll be right back with 3-3. So in 3-3, they give us the 3 strategies explicitly. They call it rewriting, looking inside, and undoing. So we kind of did all 3 in the course of 3-2. So now it's saying these strategies and others will be useful throughout the rest of this course. Examine how each of the strategies can be used to solve the equation below by completing parts A through C. At this point, with A through C, we are really just identifying which strategy is being used by each person. So in part A here, Ernie, well, first off, we have this equation here, x minus 5 over 4 plus 2 over 5 equals 9/10. And it starts off by telling us that Ernie decides to multiply both sides of the equation by 20 so that he gets this thing. So what strategy does Ernie use? Well, it looks like Ernie, actually, I'll give it its own heading here, so A. So it looks like Ernie used the rewriting method. And I can tell because now he effectively removed all the denominators, making the equation easier to work with. He removed all of the denominators, but still has an equivalent equation. And then B, it says L takes Ernie's question, decides to subtract 8 from both sides to get that. What did she use? It looks like she undid. So L is using the undoing method. She removed the 8 from either side by doing its inverse operation. And then the last person, Eric, what's up with all these E names? Eric looks like he's using looking inside. He used looking inside because he plugged in what he suspected to be the answer and got 10 as his inside result. So it looks like these 3 end up using one of each strategy to solve this equation here. So again, don't feel like you have to use one the entire way through. Sometimes you just get to a certain place and then you can kind of see it coming. So sometimes that helps, just different equation solving strategies. Cool, I'll be right back with 3-4. In 3-4 here, it says Graciela is trying to solve the quadratic equation that, and she says, I think we need to use the quadratic formula because of the decimals. She tells Walter, and then he says there's probably another way. So let's see what we can do here to rewrite this equation to make it look a little bit more palatable. So, oops, yeah, that's an x right there. And then minus 1.5 equals 0. First thing I'm going to do to get rid of the decimals is I think I'm going to multiply the whole shebang by a 10, giving me 10x squared plus 25x minus 15 equals 0. And what it does is that gets rid of the decimals, which makes it a little bit better. Now, it does now say rewrite the equation again so that it can be solved without the quadratic formula, because right now these numbers are large, but let's see what we can do to make the numbers a little bit smaller. I see that they can all divide by 5. So if I divide the whole thing by 5, what I get is 2x squared plus 5x minus 3 equals 0. Now they are suggesting that this is solvable without the quadratic formula, which means it is probably factorable. So I got 2x here and x here. I'm going to slam down a 3 and a 1 because the 2 times 3 will get me 6, 1 times x will get me 1. That can get me a 5 as long as the 6 was positive and the 1 was negative, giving me x equals 1/2 and negative 3. And so from here, this is just another example of a way to rewrite an equation so that you can not have to worry about using any kind of technology if it's not available to you. And the last thing that I want to cover today is is the notion of being able to what we call rewrite using what's called a U substitution. Now, a U substitution in these cases is not something that I use very often once I start getting used to it, but it helps definitely make an equation a lot more palatable to understand. And so from here, if you have this m squared business minus this, first off, I'm going to just subtract 6 from both sides. All right, so I have m squared plus 5m minus 24 squared minus m squared plus 5m minus 24 minus 6 equals 0. Again, I just subtracted the 6 from both sides. So here's what I'm going to do. I am actually going to say, I'm going to say on the side here, let u equal m squared plus 5m minus 24. Now, why did I do that? It's because instead of this whole nasty thing being squared, I really just have u squared now. Minus, because the minus was always there. Again, this whole thing here, which is exactly like the one before, u, and then minus 6 is equal to 0. This is a now rewritten, a lot more palatable equation to solve because we have done this several times in Integrated 2, where we have u minus 3 times u plus 2, and now what I get is u equals 3 and u equals negative 2. But again, we weren't solving for u, so I want to make sure we're very clear about this. We were never solving for u, so these are not your answers. From here, I'm actually going to re-plug back in the m portions. So u really was m squared plus 5m minus 24, and that equals 3. And then here, m squared plus 5m minus 24 equals negative 2. So now from here, how do I solve this? Well, I'm going to go and just first off make a little bit of space here on the side here. I'm going to go and subtract 3 from both sides. I'm going to work on this dude first. So m squared plus 5m minus 27 equals 0. And that's going to require the quadratic formula. So that's going to be m equals negative b plus or minus the square root of b squared. So 5 squared minus 4a, which is 1c, which is negative 27, all over 2 times 1. So after doing a little bit of stuff here, you end up getting negative 5 plus or minus the square root of, looks like 25 plus, looks like 108 all over 2. So m equals, in this case, negative 5 plus or minus root 133, and I'm just about to run out of space here all over a small little 2 right there. I apologize for the lack of space. Now that's one side of this. One side of this is being done now. The other side of it is this portion here that equals -2. So I'm going to go and just change to green here. And so what I really have here is I have m squared plus 5m minus 22 equals 0. Again, I just added 2 to both sides. So again, the quadratic formula comes into play again. So m equals -5 plus or minus the square root of b squared, which is 5 squared, minus 4ac, which is -22, all over 2a, which is going to be -5 plus or minus the square root of, looks like 25 plus 88. And so 25 plus 88 is going to be 113. So this is all over 2. So -5 plus or minus root 113 all over 2. And there are 4 solutions to this problem here. So again, the notion of the u sub allows us just to see this in a little bit better of a way. So I'm going to go and do another example real quick. Let me just go and clean up the board real quick. Actually, I'll be right back. Okay, and so now from here, let's take a look at b real quick, because it says it's x to the 2/3 minus x to the 1/3 minus 56 is equal to 0. And so whenever you see this double half relationship here where the leading term is twice, or the leading term's exponent is twice the value of the middle term's exponent, you are very likely dealing with a quadratic expression here, or a quadratic style expression. So notice how C is like 6 and 3. D actually does follow the same pattern because it's 1 and 1/2, but I'll talk about that in a little bit. So with b, what I'm going to do is I'm going to rewrite this thing using a u sub. Now again, as you get more and more comfortable with this, a u sub may or may not be necessary, but I'm going to go and call him x to the 1/3 squared minus x to the 1/3. Again, I don't need to raise him to any other power here. Minus 56 is equal to 0. And now from here, I'm going to say let u equal x to the 1/3. And now what that allows me to do is it allows me to say u squared minus u minus 56 is equal to 0. And again, here we are, we're back in integrated 2. So u minus 8, u plus 7. So u equals 8 and u equals -7. But again, we weren't solving for u the whole time. We were solving for x. So now I got to replace this with x to the 1/3 equals 8. X to the 1/3 equals -7. So I'm going to go ahead and cube both sides here. Now that's going to be kind of an odd number here. 8 to the 3rd power is not something that we readily know. That's going to be 512. And then 7 is going to be -343 if I cube both sides. Okay, I think that might actually do it for this lesson here. The rest are pretty much the exact same pattern, but as always, please leave comments or questions in the comments area. I will see you all in the next episode.